When the rate of the forward reaction is equal to the rate of the reverse reaction, we say that the reaction has reached equilibrium. Many chemical and physical reactions are reversible, which allows products to become reactants and vice versa. A perfect example of this would be the Earth's water cycle, which is in constant equilibrium, with 98.26% locked up in the oceans, lakes, rivers, and streams, 1.74% are found in the ice caps, and a very small percentage, 0.001%, is found in the atmosphere. Moving towards the right would make it an endothermic reaction, so changing something from solid, liquid to gas means that it has to absorb heat. Whereas if you move in the reverse direction, going from gas to liquid to ice means that heat has to be given off. It's exothermic. We can make the equilibrium go in a certain direction. We're said to be favoring the product side if it moves towards the right. So in this case, if you increase the amount of heat, obviously it's an endothermic reaction and you would move towards the right. Ice would become liquid, liquid would then boil and then become steam. However, if you cool the system, the equilibrium would move towards the left. It's now an exothermic reaction, and you're said to be favoring the reactants. What has more life, the Arctic Ocean or the tropical oceans? It might surprise a lot of people, but tropical oceans are actually devoid of life. The higher temperatures actually cause oxygen to bubble out as a gas and escape the water, whereas colder temperatures allow the water to retain more oxygen and dissolve more oxygen, thus supporting more life. Things like krill and plankton. That's why when you look at the Arctic Ocean, it appears darker because there's a lot more life teeming beneath the surface, and because you have more plankton, you can then support a bigger food chain and food web. Massive fish die-offs occur in warm waters. So near power plants, when they start dumping their excess heat into lakes and streams, this causes the dissolved oxygen to bubble out as a gas. So if you increase the heat, you're going to favor the right-hand side or the product side of the reaction, like how it's shown. So I intentionally made the arrow bigger to represent how the reaction is favoring the product side. If you increase the heat, you have more oxygen gas, which escapes the water. If you have lower temperatures, the fish are fine because you have dissolved oxygen in those lakes and the streams where they live. On the screen there is probably the most important chemical reaction of the modern world. It is the Haber process, and it shows how ammonia is produced from hydrogen and nitrogen gas. The ammonia is a plant fertilizer, and it's allowed countless amounts of crops to be grown for billions of people across the world. There is an abundance of nitrogen found in the Earth's atmosphere. The only problem is plants can't break down the triple bonds found in nitrogen, and if they can't do that, that means they can't use nitrogen for their growth. The other problem is nitrogen gas does not combine with hydrogen gas to form ammonia naturally, so this process has to be coaxed or man-made. You have to force it to go to the product side to produce more ammonia, and this process was developed by Fritz Haber. Haber found that under high pressure and high temperature conditions, you would force hydrogen and nitrogen to combine in a reaction, and it would favor the product side, thus producing more ammonia in the process. Let's think about why the Haber process works to produce more ammonia. So if I increase the pressure, that really means I'm decreasing the amount of volume or space that I have. Right? Because the two are inversely related. It's Boyle's law. Increase the pressure, volume goes down. So less volume, less space. If I have less space, I have less room to accommodate the molecules of gas that are present. So pretend that this occurs in some sort of reaction vessel or some sort of container where you have nitrogen gas and you have hydrogen gas and you're trying to get it to combine to form ammonia. So if you count the moles on the left, you have a total of 4 moles of gas. And then on the right-hand side, you have 2 moles. So if I have less room, that means it's going to favor the side with only 2 moles because you're squeezing the nitrogen and the hydrogen gas together. You're also heating it up too. You're increasing the amount of heat, so it causes more and more collisions. And then in the process, you get more ammonia to be produced. So if you have less room, you can only accommodate a certain number of moles. So less room, less moles. As shown in the Haber process and all the examples that I've discussed so far with the water equilibrium and the dissolved gases, if you make any sort of changes to the system's temperature or pressure or volume or concentration, it's going to shift the direction of the equilibrium either to the reactant side or the product side, and it really depends on how it's written. So this is something that you just have to do a few examples and then you'll get familiar with it. It's just a little counterintuitive at first because remember, everything in chemistry always seems a little bit backwards. So I'll keep illustrating with more examples and then you'll understand Le Chatelier's principles. Another way that we could study the equilibrium of a reaction is by setting up something known as KEQ. So KEQ is really just the concentration of the products divided by the concentration of the reactants. So if KEQ is greater than 1, it's going to favor the products, and if it's less than 1, it's going to favor the reactants. So this makes sense because to get a KEQ bigger than 1, on top, you would need the products to have a much greater concentration than what's on the bottom. To really understand Le Chatelier's principles, to understand how temperature, pressure, and concentration causes an equilibrium to go in a certain direction, we'll study this example. So we'll look at how clear exhaust becomes brown smog on a warm day. I have 2 equilibrium tubes here, both containing NO2 or the brown smog that you see there. But you're going to see that if I take one of the tubes and submerge it under ice, the temperature starts to decrease and then it starts to shift the reaction towards the side with N2O4. So that's the clear exhaust. So the brown haze will slowly disappear, it starts to fade. And there's a rhyme that can help you understand this. So warm in LA means brown hazy day, because if I add heat to clear exhaust, it shifts the reaction towards the left and you start producing more NO2. So let's really try to understand Le Chatelier's principle. And remember, all that it is if you add some sort of stressor to the system, it's always going to want to offset that change. So we'll look at this equation again. It's the one with the brown smog turning into clear exhaust. And this is exothermic the way that it's written because you see heat written on the right hand side of the equation. So NO2 is brown, N2O4 is clear. The KEQ for this reaction is always the products divided by the reactants, the concentration of the products. So you have bracket N2O4, that's a product, divided by the concentration of NO2, that's a reactant, and the coefficient in the balance equation just becomes an exponent. So make that a power of 2. So that's how you write KEQ, and we'll examine KEQ in just a moment. But I just want to point out heat is actually a product in this equilibrium. So if you cool this reaction, which way would the equilibrium shift? And it's actually going to shift it to the right because you're losing heat. You're cooling the reaction down, you're losing heat, so as a result, the system will be like, all right, brown smog, let's become clear exhaust and let's move towards the right because we're losing heat. Because it wants to offset this change. Okay, that's what Le Chatelier's principle is. It's kind of like a seesaw effect. Okay, you're always trying to balance things constantly. However, if you heat this reaction, it's going to move it to the left because now you have all this excess heat in the system. You're adding heat. This allows the heat to react with N2O4, the clear exhaust, and it turns it brown. So remember that rhyme that we spoke about just seconds ago. Warm in LA, brown hazy day. So it's going to shift it towards the left to create a brown gas. Okay, because when you have heat, when it's warm in LA, there's this brown haze that drapes over the city. And that's because of the NO2 being produced. It's all the clear exhaust all of a sudden undergoing this equilibrium shift. If you increase the pressure on this reaction, which way would it shift? So increasing the pressure, think about it, you're clamping down, right? Increasing the pressure means you're also decreasing the volume. So if you decrease your volume, you have less space. If you have less room, you can only accommodate the side with less moles. So less room, less moles, not enough space. Let's count them up. Let's look at the balance equation again. The left-hand side has 2 moles. The right-hand side has just 1. And you wouldn't count heat in this. So it's 2 versus 1. Which side is it going to shift? It's going to move to the side with less moles, which is on the right-hand side. So it would favor the production of more N2O4, or clear exhaust. If you increase the volume on this reaction, which way would it shift? So let's draw a before and after. Here's my reaction vessel or container. Okay, if I expand this container, and let's just say NO2 and N2O4 in this container, okay, which way would it shift? So now you have more room because you've expanded your container. So because you have more room, you can actually accommodate more moles of gas. So it's going to shift it to the left. It's going to favor the side with the brown gas, with the NO2, because that side has 2 moles. The other side has just 1. So again, Le Chatelier's principle always tries to offset the change that occurs in the system. It's like a seesaw effect. If the bottle in this reaction suddenly turned brown, would you assume the bottle was being warmed or cooled? So this one is obvious. It's being warmed up because it's just like our rhyme. So warm in LA, brown hazy day, because now you're adding heat. There's this increased amount of heat. So to offset that change, it's going to kickstart the reaction and start changing it back into reactants so that the heat is being removed. So you get more and more brown gas. And then to answer the next question, are we increasing the pressure or is there less pressure? So because the bottle is turning brown, that means it's moving to the side which has 2 moles. So there is less pressure. Okay, it's kind of strange to think about, but less pressure means there's more and more room. So if you have more room, you can accommodate the side with more moles. And the side with more moles has 2 on it. The other side has just 1. So a pressure question is really a volume one in disguise. So you're favoring the side with more moles because there's less pressure. Let's think about the KEQ for this one. So KEQ is 1.2 times 10 to the negative 5. What color would the gas be? So the number 1.2 times 10 to the negative 5 is a number that's much less than 1. So if it's less than 1, it has to favor the reactant side. So because it favors the reactant side, it's going to be brown. Because remember, the KEQ is always written as products divided by reactants. So if your reactants are very large in concentration, you're going to get a number much less than 1. So let's think about the next one. What would the KEQ be if you wrote it in reverse? So now you have N2O4 plus heat, and it makes the brown NO2 gas. So our KEQ would just be the inverse. It would be 1 divided by 1.2 times 10 to the negative 5, and the number doesn't really matter. Okay, you can crunch that in a calculator, but you're going to get a really big number, a number much bigger than 1, and because the KEQ is greater than 1, you're going to favor the product side, which again, now that it's on the product side, it's going to favor the formation of NO2, and with heat shown on the reactant side, this reaction is now endothermic. Le Chatelier's principle is the biggest idea in equilibrium. So in equilibrium, the reaction can either shift to the products or the reactant side. The products are synonymous with the right-hand side. The reactants are synonymous with the left-hand side. So there's a few stressors or changes to the system that can cause it to shift. So those stressors might be changes in pressure, changes in volume, or changes in temperature and concentration. If you add more stuff, let's say you add more NO2, it's going to shift it towards the other side to produce more N2O4 to create this sort of equilibrium or to maintain the balance. That's what Le Chatelier's principle is all about. So if you decrease the volume, it's always going to move to the side with less moles because you have less room, so you can only accommodate a certain amount of moles. So that's what Le Chatelier's principle does. It just offsets the change, and that's really all you have to understand for this unit. Thanks for tuning in, and I'll see you next time on Wind Chemistry.